Hello everyone, this is section 15.5, triple integrals. We're going to start with a few examples of just the mechanics behind how to evaluate triple integrals, and it's really just an extension of double integrals. So remember, we work from the inside out, so with regards to this particular integral, notice all the limits of integration are constants, but the first variable we're integrating with respect to is x. So I'll just recopy the integral from 0 to 3 and the integral from -1 to 0, and then integrating with respect to x, we get 1/2 x squared over 2, however you like to think of it. Y is held as a constant, so 2x integrates to be 2x squared over 2, so just x squared, so plus x squared y. And then 4z is a constant, so we just pick up the x, so 4xz. And that's all evaluated. And it might be a good idea just to kind of bookkeep and keep track of things to say as x goes from 1 to 2. Or you don't have to say x equals 1 and x equals 2. You could just keep it in mind that you're going to evaluate with respect to x to begin with. But in any event, then the dy dz is going to tag along. Okay, so now the fundamental theorem of calculus, so we'll recopy integral 0 to 3, integral -1 to 0, and I use big brackets here. So a 2 goes in for x, so that gives us 4 times 1/2 is 2, and then we have plus 2 squared is 4y, and 2 goes in for x again, so that's 8z. And then minus lower limit goes in, so now x is 1, so that gives us 1/2 plus y and plus 4z. And then that's with respect to y and with respect to z. Okay, probably most advantageous to clean things up inside the set of brackets there, so recopy again the integral from 0 to 3, integral -1 to 0, and then C2 minus 1/2 is 3/2. 4y minus y is 3y, and 8z minus 4z is 4z. And then again, with respect to y, with respect to z. Okay, so now we continue, and we're going to evaluate we're going to evaluate this integral now with respect to y, so again, work from the inside. So recopy the integral from 0 to 3, integrating with respect to y, get 3/2 y plus, this would be 3y squared over 2, so then we write 3/2 y squared, and then plus, integrating 4z is a constant, so we just pick up the y, so let me write plus 4yz, and then if you like, you could say as y goes from -1 to 0, and that's going to be with respect to z. So then fundamental theorem, 0 to 3, use some brackets, 0 goes in for y, so I'm just going to say a big 0 here, and then minus a -1 goes in for y, so that would be 3/2 times -1 plus 3/2 times -1 squared, and then plus 4 times -1 times z. And this is all going to be with respect to z. And then it looks like this is unfolding rather nicely at this point, because we've got a -3/2 here, and then this positive 3/2, because we're squaring this -1, makes 0. And this negative distributed would make this a positive 4z. So it looks like we just get the integral from 0 to 3 of 4z with respect to z. And now that's 2z squared, evaluated from 0 to 3, which would be upper limit 2 times 3 squared, minus lower limit 2 times 0 squared. So that's 9 or 18 minus 0, or just simply 18. Okay, so that's the mechanics behind it. Now we introduce some variables involved as the limits of integration. And so, same idea, just pay attention to the, the order of integration as denoted by the differentials. Okay, so here we copy integral 1, 0 to 1, that is, integral x plus 1 to 2x, and then we're integrating x with respect to y. So x is held as a constant, so we just pick up the y variable. So we get xy, and that's evaluated. You might want to say what variable, right? So y equals, we just integrated with respect to y, so y is z. Y is going from z to x plus z. And then that's going to be with respect to z next, and then with respect to x at the end. Okay, move down here, fundamental theorem of calculus. So we copy integral 0 to 1, integral x plus 1 to 2x, and my upper limit goes in. So I've got x times upper limit's x plus z, and then minus lower limit goes in, which is z, so minus xz, and that's with respect to z, then with respect to x. And here it works out rather pretty, because distributing the x, you get x squared plus xz, then minus the xz, so the xz's cancel, so we just get x squared. So the integral from 0 to 1, integral x plus 1 to 2x of just x squared now, with respect to x. And, I'm sorry, with respect to z, then with respect to x. Okay, so now we're integrating with respect to z, and x squared would be held as a constant, so you just pick up z variable. So we recopy the integral 0 to 1, and we have x squared z, and that would be evaluated as z ranges from x plus 1 to 2x, and then that's going to be with respect to x, and then our fundamental theorem of calculus, integral 0 to 1, okay, upper limit goes in, so we can use brackets now, z is 2x, so x squared times 2x, minus lower limit goes in, z is x plus 1, so x squared times x plus 1, all with respect to x. Okay, so just instead of doing this mentally, I'll show it literally, but we should be able to get this mentally, but it'd be 2x cubed minus x cubed minus x squared, all with respect to x. So that's the integral from 0 to 1 of just x cubed minus x squared with respect to x. And so then integrating, we get 1/4 x to the 4th minus 1/3 x cubed, all evaluated from 0 to 1. Okay, so 1 goes in, so 1/4 times 1 to the 4th minus 1/3 times 1 cubed, and then from that subtract. The lower limit goes in, but the lower limit's 0, so I'm just going to write a big 0. And so we get 1/4 minus 1/3, and that would be a negative 1/12. Okay, so that's the mechanics behind triple integrals with both constants and variables involved as the limits of integration. Next thing is the concept of integrating over a rectangular box. So we've got x, y, and z ranging between constants. These are assumed to be constants: a to b, c to d, and k to l. So we use k to l because the next thing would be e and f, and you don't want to mix up the f and so on. So they chose k and l. In any event, it's just if you're going to take the triple integral over this region G of a function of x, y, and z with respect to v, the volume, three-dimensional, then it's just going to be the limits of integration. Okay, you want to set up the dz, dy, dx, or any order that you want, really. But you want to set those up first before you denote the limits of integration, because you want to make sure that dz corresponds, the inner differential, in this case dz, corresponds to z's limits of integration, which are k to l, which are here, and the next variable is y, and those limits are integration c to d, which correspond directly, and then the outer limits are with respect to x, which goes from a to b. So you probably want to set up the differential first, and just denote that dv is dz, dy, dx, or any combination. We can alter the limits of integration, so there's actually 6 possibilities. So you could say dx, dy, dz, dy, dx, dz, etc. So an example of that. So we have to evaluate this triple integral of this function over the volume, and we're given the limits of integration there. So let's set this up. Okay, once again, I'm going to just write down the triple integral, recopy the 12x y squared z cubed, the function, and then pick an order for the differentials for dv. And I'm just going to use dz, dy, dx. Okay, now I'll fill in the limits of integration. So the inner limits are z, because dz is the first, so that's 0 to 2. Second limits are with respect to y, that's 0 to 3. And then finally the outer limits with respect to x, -1 to 2. Alright, so fairly simple in terms of setting up the integral, and now we just need to grind through the calculus. So first off, integrating with respect to z, recopy -1 to 2, recopy integral 0 to 3, integrating with respect to z, the 12xy squared is a constant, so z to the third integrates to be z to the fourth over 4. 12 over 4 is 3, so let's go with 3xy squared z to the fourth, and that's evaluated as z goes from 0 to 2, and then with respect to y and with respect to x. And then the fundamental theorem of calculus, recopy integral -1 to 2, integral 0 to 3, and upper limit goes in, so 3 times 3xy squared times 2 to the fourth minus lower limit goes in, I'm just going to write a big 0, and that's with respect to y. Then with respect to x, and 0, of course, because z is 0, so max everything out. So we just get, what's this, 16 times 348. So let's recopy integral -1 to 2, integral 0 to 3, we have 48 xy squared. Now with respect to y, and then with respect to x. Okay, so now we're ready to integrate with respect to y. And we get 48x tags along, y squared integrates to be y cubed over 3. And 48 divided by 3 is 16. So let's recopy. First integral, -1 to 2. Now we get 16 x y cubed, and that's all evaluated as y goes from 0 to 3. And then it'll be finally with respect to x. And now the fundamental theorem for this, -1 to 2. And we have the upper limit goes in of 3. So 16x times 3 cubed. And then minus lower limit goes in, but that's a 0 again, so we'll just say -0. That's with respect to x. Okay, so 3 cubes 27 times 16, probably want to use a calculator there. And it comes out to 432. And we have the x, and this is with respect to x. So now finally integrate that. We get x squared over 2. 2 goes into 432. 216. So 216x squared. This is evaluated. I was going to say -1 to 2. I mean, you could say x equals -1, x equals 2, but no need for that, really, because x is the only variable left. So then upper limit 216 times 2 squared minus 216 times -1 squared. So we get, probably want to use your calculator, but you can check my arithmetic here. 864 minus 216 over 648. Okay, so now a special equation that you want to definitely be familiar with from this point on and be able to identify it immediately. Maybe not so much this intercept form for a plane, but we do know that the equation of a plane, if you recall, comes from the normal vector and a point. And the coefficients of the x, y, and z respectively are the normal vector. And then we've got, like if the point were 2, 5, 7, it would be x minus 2, y minus 5, z minus 7, or something like that. And then you manipulate it around to get this standard form for a plane. But please be able to recognize a plane as being just x, y, and z. Any combination of signs. Okay, these happen to all be positive. But recognize a plane, and we can sketch the plane easily in the first octant. Okay, the first octant would be where x, y, and z are all positive. If we obtain this standard form. And so the standard form is obtained by just simply dividing by, setting it equal to 1, by dividing by whatever the number is on the left-hand side here. So we're going to divide everything by 12. So this becomes x over 4 plus y over 6, and then plus z over 3 equals 1. And then we could sketch the plane easily. So we got x and y and z, of course. And the values underneath their respective variable is the intercept on that axis. So 4 units in the x direction is an intercept. 6 units in the y direction is an intercept. And 3 units in the z direction would be an intercept of the plane. And then the plane, basically, if you're just drawing it in the first quadrant, you just connect those points like you would a triangle, but you can see it's, it's slicing in that direction. And this is what we typically refer to as a tetrahedron. Okay, when we draw that portion of the plane in the first quadrant. Okay, let me label this and label this as 6. So that's the sketch of the plane in the first octant, and again it's referred to as a tetrahedron. But its projection in the xy plane we're going to be interested in, as we'll see in the next example. So if we just consider what it looks like in the xy plane, it intercepts the x-axis at 4, and it intercepts the y-axis at 6. Guess I'll give myself a little bit more room, because it's kind of looking pretty, so I don't want to mess it up. Okay, so that would be 6. So this would be the projection here in the xy plane. Okay? And so that, if you will, is a little shaded area there. And we would want to know what the equation of this line is. And just simply use the fact that the slope is change in y over the change in x, because it's a straight line obviously. Change in y is 6, change in x is 4, so 3 halves. And the y-intercept b is 6, where it intercepts the y-axis. So just give it in initially, it's probably easiest just to, because you have these intercepts, easiest to just express that equation in slope-intercept form. And then if we have to manipulate it from there, we'll do so. But the initial equation, probably easiest just to, once again, give the slope-intercept form. Okay, so next we're going to look at, and we'll just talk about this theorem, and then we'll come back and we'll finish up this lesson. We're going to look at volume as a triple integral. And so it's the volume of a region that's bounded above by a function called z2 and below by a function z1, both functions of x and y, of a particular, over a particular region. So it might be a situation, as we're actually going to see in the next example, like what we sketched out here. I think different numbers, but same concept. So the important thing to realize here is that the volume really is dz times the area. The differential volume is really dz times the area, because it's dz dx dy, or dz dy dx. Doesn't matter the order, remember. But the function that we're integrating is really just the differential dz. We don't put the function in here, because the function is determined by these limits of integration, okay, the g functions, as we're going to see. So this gives a little procedure as to how to go about setting up this integral, and it's basically just find the equations for z1 and z2. Those are going to be the limits of integration with respect to z. We're going to set up the rectangular region in the xy plane, so that'll be similar to what we just went over here. And then those are going to determine the limits of integration for these two remaining integrals, the dx dy integral. Okay, so we'll come back and we'll look at an example of that, and then one other to finish off this section.